and I'm very fortunate to introduce my first senior design group ever. So they had a lot of fun with me this semester. Jad Lebavna over on your left and Justin Wolford will talk to you about the senior design project they had to go through this semester.
Thank you, Dr. Koplowski. I'm Justin Wolford, and this is my partner,
Jad Lebavna.
and we're here to talk about our senior design project, the wireless motion tracking system for rehabilitation. So, did you all know that every year 2/3 of all occupational injuries reported were due to repeated trauma of the wrist, elbow, or shoulder? That over 460,000 carpal tunnel surgeries are performed annually, and that they account for $1 billion in total costs alone. Musculoskeletal disorders affect 7% of the United States population and account for 14% of physician visits and 19% of hospital stays, and that over 5 million sports-related injuries occur every single year. So, to address these issues, our objective this semester was to design and fabricate, implement an initial prototype device to monitor motion of the human body that will be used to improve the diagnostics in the field of physical therapy. So today we're going to be discussing many things with you. We're going to begin by discussing what physical therapy is and the current standard for rehabilitation and physical therapy. We will suggest that there's a need for a better tool to monitor patient recovery. We will propose our testing criteria for our device, discuss the fabrication and design of the wireless motion tracking system, discuss the data that we acquired, conclude, and then open it up for questions. So a little background about physical therapy. Physical therapists essentially help patients who've suffered injuries to improve their mobility, in many cases getting rid of the need for expensive surgeries and reducing the need for medications. And they also work with patients to ensure that they don't suffer these injuries to begin with. The types of injuries that physical therapists look at are called musculoskeletal injuries. These are due to strenuous activity, and they include repetitive motion in the workplace, sports-related injuries, broken, fractured bones, post-operative injuries, tendinitis, carpal tunnel, sprains, fractures, this sort of thing. So the current standard, the current way they treat these types of injuries is with stretching and strength exercises. Essentially, the exercises target specific areas of the back, the lower shoulder, the arm, wherever the affected area is. And they focus on rehabilitation by stretching, flexion, and extension. And one of the things that physical therapists look at is called range of motion. And essentially, range of motion is the normal degrees of rotation of a joint. And you can categorize this in two different categories here. Abduction and adduction, which is motion pulling your arm away from the midline and motion pulling your arm back toward the midline. And in the diagram here, you can see normal range of motion for a human shoulder. But the problems with this current method is it's very subjective. Often patients who come in will have a 0 to 10 scale. Oh, I hurt this bad. It's also inconvenient for them to go to the physical therapist. They're confined to a test area there. And a big deal is patient compliance. And basically, the physical therapists do not know whether or not the patients are really actually doing their exercises or not.
Some of the available motion tracking systems on the market are optical systems. They are very accurate. They're normally used in the animation movies. Some of the other systems, like this one here, inertial systems, they are available on the market, but their constraints is size, and that's one thing we'll talk about when we talk about our project constraints. So again, our objective was to create the first working wireless motion tracking system prototype that will facilitate improved diagnostic in the physical therapy field by removing patient compliance and by monitoring range of motion in physical therapy patients. All that while maintaining a small footprint of under 25 millimeters in diameter. Some of the customer requirements that we had for this project were to create this device to track human motion. This device will provide the acceleration data to begin with and maintain a small size, smaller than a coin cell battery. And we needed to use the NRF 51822 Nordic semiconductor. We do have some secondary requirements. This device should be capable of using Bluetooth communications and should have a low power consumption. So we devised some testing criteria for this prototype. We needed to acquire acceleration data in a plane of motion and show that this data can be used in rehabilitation analysis. So here we have our system block diagram. It consists of 4 main components. We are not going to go into the power source. The power source will be a coin cell battery, and the antenna is a discrete component that will be added on at the end of the project. So we're going to go into depth about the sensor and the microprocessor. For our sensor, we are using the NRF 51822 made by Nordic Semiconductors. Some of the features of this microprocessor, its size, it's 6 millimeter by 6 millimeter. It does have flexible GPIO configuration that will help in the layout and design of this device. GPIOs are general purpose input-output pins. This microprocessor has a digital interface, the I2C communications that we will use in this device. It does have a wide supply of voltages, 1.8 to 3.6. Those will come in handy when we consider the power consumption. It also does have a built-in Bluetooth transmitter and receiver for our wireless communication, and its flexible power management schemes. As for our sensor is the LSM60S0 made by STMicroelectronics. Some of the features of this sensor, it collects 3D accelerometer and gyroscopic data. It's wide voltage that is similar to the microprocessor we're using, so that comes in handy. It does have power modes to address the power consumptions. And it does have 3 independent acceleration channels, as we see here in the center. It's X, Y, and Z coordinates for the acceleration, and the same thing goes with the angular rate data. And also, you can see it's small size. It's 3 by 3 by 0.86 millimeters.
So now that you guys know a little bit about the 2 sensors that we'll be using, or rather the microprocessor and the sensor, I'm going to talk about the fabrication process a little bit. So essentially what we do is we take these chips and we put them onto printed circuit boards. We actually manufacture them here at USI and the AEC. Printed circuit boards are essentially just like a small electronic circuit made of a conducting material such as copper in our case. Like I said, we'll take the chips and put them on the conductive material and create circuits with them. Here's a picture of the machine that we use to create the PCBs. It's called the QCJ5 quick circuit. So essentially, what we do is we create a layout in a program called Altium of a PCB, and then we export it into another program called IsoPro, which communicates to this machine. And it takes a sheet of copper, 80 mils thick, and basically shaves away the top layer of copper, leaving behind what are known as routes or traces to make an electronic circuit, and can also drill holes that we'll use for pinouts. So we broke the fabrication process down into 4 main steps. Step 1 was to just test the functionality of the LSM sensor. Step 2 was to design a printed circuit board of just the sensor alone, and then the 3rd step was to test the functionality between the sensor and the microcontroller, and then the last step was to combine them together. So step 1, here's the X-Nucleo evaluation kit. It is manufactured by STMicroelectronics, who makes our sensor, and as you can see here, our sensor is actually the 3rd sensor on this board. And what it lets us do is essentially just hook up into a computer via USB, and it has pre-made software made by the manufacturer that actually allows us to see data from the sensor. And as you can see here, there's actually useful data that we got from the sensor. So we did this to just ensure that the chip that we selected was going to provide us useful data, and it was good that the developer actually had this software for us. So the second step in the design was to design a PCB by itself of the sensor alone to ensure that we could actually create a functioning PCB design. And here you can see on the left is the LAN pattern or the layout provided by the manufacturer and the data sheet for the sensor. Those dimensions are in millimeters, so this is a very small design. On the right, you can see the layout that we created in Altium. We've also included traces in the, right here you can see the routes or traces connected to pins. And these pins are holes that we'll use for pinning out to test the sensor's functionality. And here's the result. You can see it looks just like the schematic in the previous slide. You can see that we've soldered wires to the pinouts, and what we ended up having was successful data transmission between the sensor and the evaluation kit's microprocessor. So then we tested the, now that we tested the sensor, the important thing was to test functionality between the customer required Nordic microprocessor. We've already showed that the sensor could work with the manufacturer's pre-made microprocessor evaluation kit, but we wanted to test it with this microprocessor. And so that actually required some coding, some software writing, because it wasn't provided by Nordic. But the result was that we actually got very similar data transmission between our sensor and the microprocessor that the customer required. In this slide, you can see that we're getting lots of similar data as the previous graph that was provided by STMicroelectronics. But you can also see there's like a lot of noise. This is attributed to the fact that there's a lot of sensor noise, and we haven't added the high-pass and low-pass filters in the program yet. And so the very last step was to combine the microcontroller and the sensor into one design, now that we have tested the functionality of each individually. And so here you can see a combined schematic for the microcontroller, which is here in the middle, and then the sensor on the left, as well as all the other necessary components to complete them. And here's the result, a very small electronic circuit that combined the microprocessor and the sensor in one. However, there was a problem when combining the designs. As you can see in this picture, it became very messy. When you make these circuits smaller and smaller, there's soldering issues, broken traces, and short circuits. You have to remember, like I said earlier, these traces are small. They're 8 mils wide. That's 8 thousandths of an inch wide. So when we try and solder them, sometimes we short them or rip them off entirely. And so the 2 lines at the top are actually our data lines. And so we never were able to test the data functionality of the combined sensor. However, we did test the functionality between the sensor and the microcontroller together.
Here you can see our sensor compared to a coin cell battery in Justin's hand. One of its main advantages, its size. It's very small, and we think it's going to be very discreet for the user. It can be applied on specific areas of interest on the patient that we can collect data from that area. Its potential for low power consumption, as we talked earlier, these sensor and microprocessor have different operating mode for low power, and its potential for wireless autonomy. I should mention that the wireless features are basically blocks that can be added at the end after we connect the antenna. This system operation is basically our how the data is transferred and moved around. To begin with, the sensor itself contains the first 3 blocks. The sensor will read the data and return that value in voltage reading based on the orientation of its 3 axes. This data is then run through an ADC. An ADC is the analog to digital converter. So now our voltages are converted to digital values. Now those values are stored in the sensor, And here is where we come in. We used two-wire communication, I2C, to access this data and transfer it to the microprocessor for initial processing, just converting the values to human-readable numbers. After that, we export these numbers to MATLAB, which is the software we use to post-process this data to make sense of it in terms of acceleration and rotation. Okay, we had our initial testing. Here I have two videos. This graph here shows the location of our sensor. So it's basically an arrow pointing to the location so we can keep track of the angle. In this video, you can see we are testing our sensor. However, there's a certain amount of lag between the graph and the video because the data was not collected in real time. And the data graph here has a faster speed than what we actually tested. So this is one of the types of data that we are collecting. There are different values like acceleration. This here is just the angle which relates to the range of motion we're trying to assess. I'll keep this video to play. So as one of our requirements was to keep this device low cost. So for our microprocessor, the microprocessor itself costs $2.50. Our sensor costs $4.80. The battery, the coin cell battery, would cost around $2. And fabrication, we decided that it would be better to outsource the fabrication to improve the quality versus what we can make here by hand because of its small size. So a total cost of $44.30, and we think that's very good on the cost. There are some other possible usages for our wireless motion tracking system. It could be used to monitor ergonomics of the human body, maybe in the workplace. It could be used in sports medicine and athletic trainings. It could also be used in 3D motion capture and animation in conjunction with optical system for movie animation. It could be used for biomedical analysis. Also, it could possibly be used for USI engineering programs or projects like the Baja car or the high altitude ballooning. We believe that we met the requirements for our device. However, there are still some consideration for the future, such as the secondary requirements, the wireless capabilities, and the low power consumptions. However, those are very easily implemented, as I mentioned earlier. Also, we tested the data or collected the data in two axes, one plane of motion. So we would like to expand on that and do 3D axes in all planes of motion. Also, recently we learned that there's a new sensor on the market. It's made by STMicroelectronics, very similar to our sensor. It has the accelerometer and gyroscope. In addition, it will have a magnetometer that's basically a compass that would help us find our initial position when we implement the 3 axes data collection. So in conclusion, our wireless motion tracking system is capable of outputting the acceleration data we require. This data was used to show its usefulness in physical therapy rehabilitation, and it is very advantageous of other design alternatives, basically its size and cost. This concludes our presentation. Some thank yous. We'd like to thank Dr. Lubavsky for all the help he provided to us in this project, Dr. Kissel for sitting in on our dry runs, all of our USI engineering faculty and staff, friends and family, and I would like to personally thank SRG Global for our computer. and we can open it for questions.
All right, questions?
Congratulations, great job. I have a question regarding the components. You mentioned that the microprocessor and the sensor. What other, besides that microprocessor and that sensor, do you consider others?
Alternatives?
Yeah,
Alternatives, yeah.
for the microprocessor.
There was an alternative discussed in the beginning.
For the microprocessor, no.
No, not for the microprocessor, that was actually a customer requirement, but for the sensor, we discussed an accelerometer called the ADXL, and we didn't pick it because it didn't provide gyroscopic data as well, and it was the same exact size as the sensor we chose.
Okay, thank you. Speaking of future considerations, in the slide of future considerations, do you think that using that hardware is going to eliminate the lag that you have there in the video?
The lag is purely because of my lack of video editing skills. I couldn't get the timing right. But in the future, it would be real-time analysis, and the graph is just to show what kind of motion or data we can extract from it.
Okay, one last question. Did you contact one of the sports medicine doctors to talk about this prototype that you guys built?
We have not, since we don't have a functional device within the size that we needed to, but research shows that such devices are being used, and their main disadvantage is size. So we're focusing on creating a working device small enough to test it on patients. And
okay, thank you so much. I understand.
Thank you, Chad and Justin. Chad, when you showed the image of the angular motion graph, what device was providing the data for the angular motion? Was it the accelerometer? Was it the gyroscope? What was it?
it was the accelerometer, basically. And the accelerometer basically reads the acceleration based on its motion and Earth gravity. We factored out the Earth's gravity from the acceleration we're reading, and that data is purely because of the motion, or the orientation. So basically, we have a vector divided into its component, and we're able to plot that.
And what's the transmission range for this wireless device?
We have not tested that since we have not implemented it.
Very good, guys. This is an excellent presentation. If you move the component out of the biomedical range, it really has a lot of interest for me about industrial application. How did you address the vibration issue? How does it handle the vibration?
Are you referring to the sensor noise?
Yes.
Okay.
Well, sensor noise, but also if you deploy this in an industrial environment, does it survive a vibration environment?
So once the gyroscope and the accelerometer are used, there's certain methods that can be combine the data to reduce such noise, because the accelerometer itself has a certain amount of noise versus the gyroscope itself has a certain amount of drift. So basically, it's not coming back to zero. So when you combine those based on some advanced operation, that could reduce such noise.
Other questions? Go to slide 32, please. Okay. Now for a product, it's not real pretty. I was wondering what your vision is of the final product, because prototypes, you need the prototype to be functional, to be able to do all the testing that you need to be able to do to make sure that everything works. But what's your vision for this sensor when it becomes marketable? What do you think it's going to look like?
This is the prototype, as you said, it's not very pretty. Our vision is to reduce its size. My personal goal or hope for this product is to fit right on top of this coin cell battery, so that keeping the size very small. And for the future, I would see it being implemented in its small size that can be placed in let's say a pouch or a pocket on your elbow or your wrist or any part of your body. So there might be some clothing line that can use this sensor, that we can use with this sensor. Basically, this is the second step of getting it smaller, and I think we can get it even smaller than that. And like I said, there's a new sensor in the market that's the size of the microprocessor. So if you look at the number of the components, there's only 2 main components versus other products, they have more components. So we're very good on the size, and we're hoping to get it even smaller.
And you said it wasn't very pretty. That's partly due to the limitations of the machine here on campus, being only 2-sided. That is a top and a bottom layer. When we finish, we really would like to outsource this to a professional company who could make a multi-layer, up to 4 layers on this sensor. So that would do 2 things. It would make it more pretty, and secondly, it would reduce the size by adding voltage and ground planes in the middle of the sensor. So that would help us reduce the size and the overall aesthetics of the final design.
Excellent. Any other questions? All right, let's give them a hand.